Hello, I am Vibhuti Chandna and I am presenting a research paper, a slice-based estimation approach for maintenance effort by Hakam Alomari, Michael Collard, and Jonathan Meltek. Some information on the authors. Hakam Alomari is an assistant professor of computer science at Miami University. His research interests include software maintenance and evolution, program comprehension, reverse engineering, and software visualization. He has an H index of 5. Michael Collard is an associate professor of computer science at the University of Akron. His research interests include software engineering, software development and evolution, source code transformation, and differencing. He has an H index of 24. Jonathan Meltek is a professor of computer science at Kent State University. His research interests are software engineering, software evolution, and source code analysis. He has an H index of 41. So this paper was presented in the 30th IEEE International Conference on Software Maintenance and Evolution in September 2014, and this paper has been cited for 11 times. Now, in this paper, the authors introduce a maintenance effort estimation model based directly only on source code. It entails computing the slice for all variables in a system and modeling how slice changes over time. They also present a case study in which slice-based metrics are applied to 974 versions of Linux kernel. Kinda the motivation behind building this maintenance effort estimation model is that all the other models are based on and used factors which are derived from the closed source software projects. But this approach is not that useful for larger corrective, adaptive, or perfective tasks during the system evolution of open source systems. In this case, the effort of a maintenance period greatly depends on the amount of source code changes made to generate a new software version from an earlier operational version, and for open source systems, this data is not documented. Additionally, because of the nature and complexity of the maintenance tasks in open source systems, directly using effort estimation models built on closed source data comes with a lot of negatives. Since we cannot apply an effort estimation model built from a closed source system directly to an open source system, because the absence of maintenance effort data prevents validation, an alternative approach has been proposed which consists of 5 phases. Phase 1 includes identifying measures that are theoretically related to and can indirectly represent maintenance effort. Phase 2 involves extracting the maintenance data, which includes dependent and independent variables. Phase 3 involves validating the correlation between the two types of variables extracted. Phase 4 involves using multiple linear regression analysis to build the effort prediction models. Phase 5 is predicting the indirect maintenance effort based on the models built in previous phase. Two software measures that can be used to represent maintenance effort of an open source systems are lag time and source code change. First, the lag time is the sum of individual times for each maintenance task in a version of a system. An increase in lag time indicates an increase in maintenance effort. However, there is a risk of over-reporting maintenance effort, and using lag time to represent the maintenance effort is not 100% accurate. Secondly, the source code changes are committed into the change logs by developers. That means it depends on the developers who submits the changes, like how well she understands the code and how well the changelog messages are written. Most of the times, these changes are not properly recorded and documented, and therefore imprecise or blank changelog entries make it difficult to build effort estimation models and traceability links. Next, we'll talk about program slicing. It is an approach widely used for understanding and detecting the impact of changes to software. It computes a forward, static, non-executable, inter-procedural program slice for each variable in a system. The slicing process is performed using the src-ml format for source code. The authors used a tool called src slice for this. Program slicing and program analysis involves 3 parts. First part is creating a slice profile and system dictionary. The slicing criterion is the triple f, m, and v, where f is a file in the system, m is a function in the file f, and v is a variable in the given function m. This slicing criterion can be used to find all the slices of all variables in all functions in a given file. After that, a system dictionary is built, and each entry of this dictionary is a slice profile with a definite structure which includes file, function, and variable names, an index of each variable as declared in order in the function, and so on. Two definitions of the slicing criterion are presented. The first one consists of the union of static forward slices. The second definition represents the general decomposition slice for all variables in all the files F and all the global variables in the system. Next part is encoding slicing information. The system slice encoding algorithm works on slice represented by the system dictionary. The basic process of the SSE algorithm starts with a single pass through the system dictionary, where the step 1 is encoding each slice profile to a string value. In step 2, the string value is fed to a hash algorithm to produce the final results, the hashed slice encoding. Finally, the third part is to compute system behavioral change information. SRC to SRCML and SRC slice are used to build the system dictionary with slice profiles for all the slicing variables in each version, and then the encoding algorithm is applied on them. The slice hashes in the later and prior version are compared to find the behavioral changes, and then finally, the system behavioral change information for each version is saved in a database. The database includes a system change table. Each version of the system has one record in this database, and the change info field of the table contains the behavioral change information of this version compared to its prior version. The investigation of building an effort model starts by obtaining empirical data and estimating a productivity function from such data. The final empirical data involved in the estimation of the function is represented by the equation shown here. Once the productivity function is determined, the resultant model can be used to predict future maintenance effort requirements. In order to build the slice-based model, 6 measures are extracted from the source code repository, and the changes between slice hashes for each of the 974 versions. These measures are described in the given table. LOC size, file size, slice size, and S coverage are determined from the source code of the base version of Linux kernel. Hash size is determined from the change information of the evolved version. Lag time is determined according to the date differences between the base version and the evolved version. In this case study, slice-based metrics are applied to different versions of Linux kernel and then compared to traditional measures of code effort, for example, LOC. In the graph shown over here, to study the average rate of hash slices changed for files, the number of files that were added, deleted, and modified between consecutive releases of Linux versions are plotted. From this graph, if we interpret rate to mean the fraction of source code that is modified in each release, then the data seems to support the claim that work rate is almost constant. These figures show the number of releases per month for the development and stable versions, respectively. And we can clearly see that the stable versions are released less frequently than the development versions. Then, the intervals of time between consecutive releases, measured in days, inside the same major version are examined. The first figure here displays the raw data of the intervals for each version, and the next figure shows some statistical parameters of intervals for each version. Thus, after examining all the results obtained for three types of versions, development, stable, and version 2.6, an effort estimation equation shown here is tailored to reflect such differentiation in both the kinds of versions and consequently the type of activity performed, for example, corrective, perfective maintenance, etc. Using this equation for the Linux kernel, the results suggest that three types of versions should be differentiated during the calculation process of the slice-based matrix. In this study, 11 major versions containing 974 separate releases were analyzed. These models were built on data from 783 versions and then validated on maintenance data of 191 versions. The first table shows Spearman's rank correlations between dependent and independent variables. Based on this information, the indirect maintenance effort estimation models were built. The first one was built using code-based metrics, and then second one was built using slice-based metrics. These model equations are shown here. The next table shows linear regression analysis of the model. Both the models have the moderate R-square and adjusted R-square values, which implies that based on data of 783 versions, the model is accurate in predicting the indirect maintenance effort. Model validation is the most important step in the model building process. The validation of a model consists of analysis of residuals. And as shown in this table, 5 statistical parameters were calculated over 191 versions for code-based model and slice-based model. It is clearly evident that slice-based model performs better than the code-based model. These results suggest that the slice-based model using the slicing information reflects both the type and the size of the maintenance process more accurately. So, as we can see that a direct maintenance effort model using person hours for open source systems was not constructed. Instead, the proposed maintenance effort estimation model accurately determined the source code changes based only on the source code. They estimated the maintenance effort based at the amount of changes made for maintaining the system. And lastly, the analysis over all the Linux versions were performed using a lightweight forward static slicing approach.